All right, today we're pulling back the curtain on the AI you're probably using every single day. We're going to trace the entire recipe, from the raw data these things are fed, all the way to the answers they spit out, and we'll uncover the key engineering choices that make it all happen. Let's get into it.
Look, you've probably asked an AI question or had it help you write an email. And yeah, it can feel a little bit like magic, but it's not. The way these models act, their strengths, their weird quirks, even their screw-ups, it's all a direct result of how they were built. So let's figure out how they really work.
And that right there, that's the main idea for this whole thing. Every AI model is basically the outcome of a few really big design decisions. If you can understand those choices, you can understand AI.
So our deconstruction has to start at the most fundamental level, the diet. The data these models are trained on is the bedrock for literally everything else.
A huge chunk of what many of these models read to learn about our world comes from this data set called Common Crawl. And well, it's pretty much exactly what it sounds like, a giant crawl of the public internet. So that means it's not just encyclopedias and scientific papers, it's also forums, clickbait, comments sections, the whole messy, unfiltered, chaotic web. And the model learns from all of it.
Now here's where it gets really interesting, the imbalance. The internet isn't spread out evenly across languages, so the training data isn't either. English makes up roughly half of Common Crawl, and that has a huge direct impact on performance. And AI is almost always going to be better at a language it's seen more of.
Okay, so you might be thinking, just throw more data at it, right? More is always better. But what engineers have found is that's not always the case. Turns out, a smaller, really carefully cleaned up dataset can often work better than a massive, messy one, especially if you're trying to do something specific, like analyze medical records or financial reports. Curation is king. So, we have our ingredients. But even the best ingredients in the world need a powerful engine to do something with them. And that brings us to the model's architecture, the actual blueprint that dictates how it learns. For years, the main architecture people used was called an RNN. You can think of it like this. Imagine trying to answer a super detailed question about a book, but you've only read the little summary on the back cover. You just don't have enough context. The real game changer was the transformer architecture. Its big trick is something called attention, and it's like being able to instantly flip to any page in that book at any time to find the exact piece of information you need. That's why transformers took over.
But there's a catch. Transformers can be incredibly expensive to run. So engineers got clever. They came up with this architecture called Mixture of Experts, or MOE. Picture a giant consulting firm with thousands of experts on staff. When a client comes in with a question about, say, renewable energy, you don't call every single person into the conference room. You just grab the 2 or 3 experts who actually know that topic. MOE works exactly like that, making these huge models way more efficient.
And this chart shows you exactly how that works in the real world. A model like Mixtral has almost 47 billion total parameters. You can think of parameters as all the little connections and knobs in the AI's brain that get tweaked during learning. But thanks to that MOE design, for any single task, it only needs to turn on about 13 billion of them. So you get the knowledge of a massive model, but with the speed and cost of a much smaller one. It's a really clever trick. So it all comes down to finding that sweet spot, right? The perfect balance between how big your model is and how much data you feed it. Well, researchers discovered this amazing rule of thumb called the chinchilla scaling law. And it basically says that for the best results, you want to have about 20 tokens of data for every single parameter in your model. A token is just a piece of text, sometimes a whole word, sometimes just a syllable. This simple ratio is what guides engineers when they're spending millions of dollars trying to build the most efficient AI possible.
Okay, you've fed your giant model a massive dataset from the internet. So what do you have now? Well, it's not a helpful assistant, that's for sure. It's more like a really, really powerful, but also very weird, autocomplete for the entire web. The next step is to basically teach it some manners.
And this whole process usually happens in 2 main stages. First, there's supervised fine-tuning, or SFT. That's where you just show the model thousands and thousands of examples of really good conversations, great questions with great answers. Then you move on to preference fine-tuning. Here, you give the model 2 different answers to the same question, and you have humans pick which one is better, or more helpful, or safer. Over time, the model learns to copy the style it was shown, and then to create answers that people actually like.
There's this fantastic analogy for this whole process that floats around the AI community.
A Shoggoth is this fictional monster from H.P. Lovecraft. It's this powerful, alien, totally unknowable thing. Training a model on the internet creates this Shoggoth. The alignment process, all that fine-tuning, that's like putting a smiley face on it. You're polishing this powerful, deeply weird entity until it's friendly and safe enough to show to the public.
So, we've got our data, we've picked an architecture, and we've put our model through finishing school. But what about the moment of truth? When you type in a prompt, how does it actually choose the words that become its answer?
When a model is generating text, what it's really doing is just predicting the most likely next word over and over again. But here's the cool part. It doesn't have to pick the single most obvious choice every time. Engineers have this setting they can adjust, kind of like a temperature knob. If you turn the temperature down low, the model plays it safe. It becomes coherent and predictable, which is great for spitting out facts. But if you crank that temperature up, it gets more creative, more willing to take risks. That's perfect for brainstorming, but it can also lead to complete gibberish.
Okay, so let's put all these pieces together. We've looked at the data, the architecture, the alignment, and how it generates an answer. So what does this all tell us about what these systems really are at their core? This might be the single most important takeaway of all. When an AI gives you two different answers to the exact same question, or when it hallucinates and just makes something up, that's not a bug. It's not broken. It's the system doing exactly what it was designed to do. It's a machine built to sample from a giant distribution of probabilities. And that means anything that has a non-zero chance of being said can be said. That includes moments of genius and moments of total nonsense.
Now, that doesn't mean engineers are helpless. They have a whole toolbox to try and manage this randomness. They can save or cache answers to common questions, they can lock down those sampling settings like temperature, and they can fix the random seed. But, and this is the kicker, even after doing all of that, because of tiny differences in hardware and software, you still can't guarantee 100% identical outputs every time. That probabilistic nature is just baked into its DNA.
So if you want to boil it all down, this is the formula. The AI model that you talk to is the product of these four major components all multiplied together. It's the data it learned from, times the architecture of its brain, times the sheer scale of the model, times that final alignment process that gives it a personality. You change any one of those variables, and you end up with a completely different kind of AI. So you see, it really isn't magic. It's a series of very deliberate, very important engineering choices. And once you know the recipe, you have the power to understand why these tools work and fail in the ways that they do. So it leaves us with a pretty fascinating question. If you were the one in charge, calling the shots, what data would you use? What trade-offs would you be willing to make? What kind of AI would you build?